So we just learned about this ratio test and saw how amazing it is and how satisfying it is when a whole bunch of stuff cancels out. So on example 5, we have 3 examples here. Determine whether each series is convergent or divergent. We'll take it a step further. If it converges, is it absolutely or conditionally convergent? You know how we do. All right, let's come over here where we have some extra space. We might need it, just maybe. All right, we have example 5. And our first problem on example 5 is the sum from n equals 0 to infinity n squared times 2 to the n plus 1 over 3 to the n. Look at this mixture of things in it. It has a power function like this n squared. It also has exponential functions, so it's not just geometric. It has a mixture of these two things. This seems like a pretty good candidate for the ratio test. So to do the ratio test, I'm going to take the limit as n approaches infinity. The absolute value of, it's the n plus 1th term over the nth term. And we said that in the last video, the last example, what you can do is just set that up as a product instead of a quotient. It would be n plus 1 squared times 2 to the n plus 1 is n plus 2. Over 3 to the n plus 1. Right, so ordinarily this would be over the nth term, but I'm just going to basically multiply by the reciprocal. That will put 3 over n up top. N squared times 2 to the n plus 1. Boop. All right, look at our n's. Our n's starting at 0. It does make a little bit of a problem with this one over here. Are you sure that this is supposed to be n is equal to 0? Maybe that should be a 1. It makes a little bit more sense for it to be a 1 because down here I would be divided by 0. Anyways, all right. So they're all positive numbers if we take that thing out. And we can get rid of the absolute value symbols and then start canceling stuff. Like, for example, let's start with these 3's. 3 to the n and this 3 to the n plus 1. I'm going to be left with just 3 on the bottom. Okay. 2 to the n plus 1, I'm dividing this into 2 to the n plus 2. Subtract those exponents, you just get a 2 left over on top. And then nothing in terms of the n's cancel out. But notice again, everything is positive. We can get rid of the absolute value symbols. I have the limit as n goes to infinity of n plus 1 squared times 2. I'll just put the 2 up front. And then on the bottom, I have 3n squared. All right, if you were to plug infinity, you do get infinity over infinity, L'Hopitalable, or just use your pre-cal rule here, which you can see that since top is squared, bottom is squared, it should approach the ratio of the leading coefficients, which is 2/3. 2/3, that's less than 1. What does that mean? So think geometrically again. If your ratio of terms is getting closer and closer to 2/3, this thing is going to converge absolutely by the ratio test. Our sum, I'm not going to keep writing these little sums down, so I'm just going to write it like this. Or not write it like this. Converges absolutely. If it converges absolutely, that means it converges. If you take the absolute value, it doesn't really matter because all the terms here, wait a minute, let me fix this again. There. Now all the terms are positive. Let's take a look at the second one. Number 2. I'm sure there's a summation symbol in here. N equals 1 to infinity n to the n over n factorial. Okay. N to the n over n factorial. That's strange, but definitely looks like something you'd want to use the ratio test on. You've got exponentials, but it's weird exponential. And you also have factorials. Let's try the ratio test on it. Limit as n goes to infinity. Let's just see what happens. Let's just see. Absolute value of n plus 1 to the n plus 1 over n plus 1 factorial, and then we'll multiply by the reciprocal, n factorial over n to the n. Bert. Huh. I hope stuff cancels. Well, I can at least see that this cancels out with the factorial on the bottom, leaving just an n plus 1. Yeah, there's that. Ooh, look at this. This is n plus 1, and this base is also n plus 1. And we're dividing so we can subtract those. How convenient is that? It's like someone made up this problem specifically. So I subtract those exponents. I get n plus 1 to the nth on top, and on the bottom, n to the nth. All right. Well, they both have the same exponent, which means we can use the power property of exponents to rewrite it as n plus 1 over n to the nth power. This is sort of looking familiar, especially if I do this. Maybe divide n into both of these. 1 plus 1 over n raised to the n. You know what that is equal to? It's equal to e by definition. That is the limit definition of e. E is 2.7 blah, 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 which is greater than 1. Therefore, this diverges by the ratio test. Our summation, a sub n, because I'm not writing it again, diverges. Now, I'm just going to take a second here to look at this, and maybe if I look at the nth or zoom in on this for some dumb reason, nth term test for divergence. So if I were just to look at the limit as just the nth term, n goes to infinity, of n to the n over n factorial. Well, we looked at, I think, 2 to the n and n factorial, and we saw that the n factorial grows faster. Is that still the same with n to the n? Let's check it with the calculator, shall we? And I wonder if I can just pull it up from before and then change this function. Let's change this function. This 2 to the n, let's make our 2 to the x, let's make that x to the x. Let's see if it freaks out. Maybe it will, maybe it won't. All right, come on. Let me change stuff. There we go. Make that, get over here, x raised to the x power. Joop. Look at that graph, it's crazy. Okay, so let's compare this in the table here. So at first, it looks like everything is, okay, x to the x starts winning very quickly. Wow. Not only does it start winning very quickly, it stays that way. So this is e to the 14th. Let's see, n factorial right beside it is, whoa, it's not even in scientific notation. Let's look at the 20th one. This is times 10 to the 26th right beside it. Only times 10 to the 18th. What? Child's play. Let's look at the 50th. All right, so x factorial is times 10 to the 64th power. Let's see what x to the x is. To the 84th power. It's gargantuan. Yeah. So it certainly gets bigger faster, right? All right. So in terms of limit, we had graphical, actually tabular evidence that this thing grows faster. Grows faster, which means that this is equal to infinity. Which is not equal to 0, so it diverges by the nth term test for divergence. Another way to have looked at that particular problem